So you can start if you are ready.
Can you hear me? Hello. Is the sound okay?
Yes. Please go ahead.
Okay, I start. Hello, everyone. I'm Shuai from Tsinghua University. The work I'm going to present today is Dispersing over-the-air long-range CTC for diverse receivers in LoRa. The past decade has witnessed the explosive growth of wireless technologies. Popular wireless technologies contain two categories based on their communication ranges. The short-range wireless protocols, such as Wi-Fi, Bluetooth, and Zigbee, have a high data rate but are deficient in coverage. On the contrary, the long-range wireless protocols, such as LoRa, have a large coverage and low power but are limited in the data rate. These two categories of technologies each have their own advantages, but they cannot communicate with each other directly. By pushing the information from the long-range wireless to the short-range devices, we can bridge the technology gap and build more efficient IoT systems. Cross technology between LoRa and the short-range protocols is very challenging due to the following two reasons. First, LoRa signals from distant transmitters suffer from mouse-sphere channel attenuation, making the LoRa signal to be difficult to be demodulated. Second, existing CTC approaches are mostly based on physical layer signal emulation, which requires high-end transmitters and is not supported by low-cost LoRa hardware. So we propose L2X to achieve long-range close technology communication between LoRa and the Wi-Fi, Bluetooth, and Zigbee protocols. The key of LoRa demodulation is to disperse the LoRa chirps that transforms the time-varying chirp to a single-tone signal. However, the Wi-Fi, Bluetooth, and Zigbee receivers do not support dispersing LoRa chirps, so they cannot demodulate the LoRa packet. So in this work, we propose to offload the chirp dispersing from the receiver to the transmitter. Therefore, we use two LoRa transmitters for the L2X transmission. We use a data node for sending the data signal, and we also set up a help node that sends the reference chirp. When those two nodes transmit simultaneously, their signals will be surpassed over the air, and this leads to a similar effect of chirp dispersing, whereas the amplitude of the surpassed signal has the same frequency as the dispersed data chirps. Therefore, the Wi-Fi, Zigbee, and Bluetooth receivers can extract the signal amplitude through RSSI sampling and finally demodulate the LoRa packet. We implement L2X with commodity wireless transceivers, and we evaluate its performance in both indoor and outdoor environments with various distance. For the outdoor environment, the maximum communication range of L2X reaches 1.2 kilometers, and the received SNRs at all the locations as shown in the picture, where most evaluated locations have a negative SNR indicating the LoRa signal is severely attenuated and is buried in the noise. We adopted 4 metrics for evaluating the performance of L2X, and we compare L2X with the standard Zigbee and state-of-the-art CTC approaches. We use the evaluation to answer how well does L2X performs compared with the state-of-the-art. We perform the evaluation with the indoor test bed on the various SR settings and LoRa configurations. We use the USRP for transmitting white Gaussian noise, and by adjusting the transmitting power of the USRP, we can generate LoRa packets with different SNRs. Based on the evaluation, as the SNR decreases, the simple error rate of L2X increases much slower than state-of-the-art. This is because L2X disperses LoRa chirps for energy concentration, and so it can demodulate LoRa signals even with extremely low SNR. When use the LoRa configuration with SF12, we can see that L2X outperforms all the other methods and pushes the SNR threshold to -9 dB, which promises a wide coverage area. So to conclude, in this work, we propose L2X, which realizes the cross technology between LoRa and the short-range wireless protocols, making it possible for LoRa to coordinate with other protocols in the shared wireless band. L2X enables non-LoRa receivers to detect and demodulate LoRa signals, even under extremely low SNRs. And this is very useful for developing IoT systems in regions without wireless infrastructure for long-range communication. That's the end of my presentation. Thank you for listening.
Thank you. Thank you for the presentation. So questions from the judges?
Yeah, thank you. For my side, I have a question. So basically, you add some physical mechanism to enable this. So have you measured what kind of additional power consumption you have in the node due to your mechanism?
Sorry, I did not get your question. Could you
have
say
you
it again?
measured? Can you hear me?
Yes, I can hear you.
So you are adding also some hardware mechanisms, right, to the transmitter. Have you measured what additional power your mechanism uses in the transmitter?
Yes, actually, we use two transmitters for transmitting the signal to the non-LoRa receivers. And for each transmitter, the power it uses is the same as it in normal LoRa transmissions. So we did not add any extra power consumption to a single transmitter.
But you double the power consumption because you use two transmitters, right?
Yeah, yes. However, we can use a LoRa gateway as one of the transmitter, and the LoRa gateway are usually powered and usually have enough power. So it is in practice it will not decrease the lifetime of the transmitters. Right.
Okay, any more questions from the judges? If not, thank you very much. So we'll move on to the second speaker.
Okay,
so
thank you.
Yeah, thank you. So just to give you some background, so this is the SRC is the main student research competition of ACM, right? So champions, we have two categories, undergraduate and graduate. Champions of both categories will compete against the other 6 in the ACM finals. So now we move on to the second speaker. Whenever you are ready, so you can start.
Hello, can you hear me?
Yeah, clear.
Perfect, so I start. Hello everyone, this will be my presentation, which began as my master thesis and I'm now continuing during my PhD, which is about, I will talk about providing software support for a custom artificial intelligence accelerator for space processors. So the difficulties of space computing come from the space processors, which are simple, are in order, have low power, and these constraints are because we require them to be safe and to go through a qualification process for space and also to support real-time capabilities. All of these constraints make that these processors cannot keep up with the requirements for artificial intelligence. An alternative, which would be the use of commercial devices, it's challenging as these devices do not provide radiation hardening and therefore cannot be safely used beyond low Earth orbit. And also they lack qualified software stacks, nor support real-time operating system support, making challenging to implement those in a space mission. An alternative, which we have explored, is the extension of an already qualified processor with an additional module in order to have artificial intelligence speedups. This module will allow us to only have to requalify a partial of the processor, avoiding to requalify what was already used. In our approach, we used a SIMD module, which uses 8-bit integer components, reusing the integer register file. This is also in order to avoid any kind of requalification for the memory accesses. And this module is divided into stages. In the first stage, we perform parallel computing. And in the second stage, we can do reduction operations. Furthermore, we have included a control register, which we call the Sparrow control register, which allows us to set some configurations such as a mask or reordering and replicating the vector components. So in order to take advantage of all this hardware, what we did is to implement some software support. Since we are going through this extending an already qualified processor, we want to avoid any complex modifications also in the compiler in order to allow the incremental qualification. This means that we will only support the new instructions in assembly, and those can be programmed using C-line assembly in order to avoid having to code all the tests and benchmarks with assembly. We have modified two widely used compilers, which are GCC and LLVM, and we plan in the future to add more features to the compiler, but at the moment we have gone with a lightweight library in order to simplify the programming to be similar to that of SIMD intrinsics. This lightweight library is written in C preprocessor macros, and the main idea is to hide the use of inline assembly in the code. Also, we have added a variable in order to control the Sparrow control register value, reducing the complexity of using it. As you can see in the codes, we can see inline assembly in the left and using the library on the right. We can see how setting the control register is much more clear with the library. We don't need to know which bit does what. Also, we can see in both sizes that we can access the whole vector using a word pointer. This is thanks to the reuse of the integer register file. And finally, we can see that we can use in a more clean manner the library, as we do not require the inline assembly, and just pass the operands for the two stages as a function. The experimental results show that we have achieved 7 times the speed up for matrix multiplication, which increases up to 17 times when we are using saturation. We can compare in the both graphics the performance with saturation on the right and without on the left. And we can compare also GCC and LLVM. GCC is the green values and LLVM is the blue ones. Finally, I would like to mention that this project is open source, and you can find all the code for both the hardware and software implementations in the following links, or also using the QR on the slide. Thank you all for your attention, and I will be happy to answer any questions.
Thank you. Thank you for the presentation. So questions from the judge panel, please.
Yep. Thanks a lot for the talk. Very nice. You said that you modified the GCC compiler and the LLVM. So usually in space projects, these tools are qualified. I mean, you cannot officially certify them, but they are qualified mostly because they are proven in use. So if you modify them, you know, what impact do you think this has? Because you cannot argue in certification that it's proven in use with your modifications, right?
Yeah, so the idea is to keep the changes small, so we don't go into much depth, just adding the support for these new instructions. And then when we make sure that this works, we can go to every time a next step, you know, like doing more tests in order for it to be tested, and at the end it can be used in a space mission.
Okay.
I don't know. Yeah. Okay.
Yeah, I would like to ask. So your project is basically mainly a software work, right? So I have some difficulty to connect with this special.
Sorry, can you repeat the last part? I didn't.
Okay. Yeah. So, what is the specific challenge that you work for space processors, but not other kind of processors? So for building this software too.
Yeah. So space processors are mainly like embedded processors, but in a critical environment. So these need to be safe, secure, and they have to go through the qualification process. And in other areas, you can use commercial devices and GPU accelerators and similar things. But in space, this is more a challenging approach. So our idea is to try to increase the performance without having a high cost. and explore also other options to provide artificial intelligence high performance in satellites and space missions.
Yeah, okay, thank you.
All right, thank you for the presentation once again and the questions. So we'll move on to the next speaker. Well, right. So by the way, this is Wan Li. So I'm supporting this SRC from SIGBAT. So the chair, Yuan-Hao, has a parallel session to chair. So I'm hosting it on his behalf. So actually SIGBAT started this SRC quite late. So the first version was held in 2019, but not that formally. So this year, this is the first formal SRC for embedded systems, real-time and cyber-physical systems. So we admitted 19 students to the second round in both categories. Yeah, just to give you some context. So we can start the third presentation. If you're ready, then please start.
Hello, can you see my screen? Hello?
Yes.
Can you hear me?
Yeah.
Yes.
Okay, I'll start. Hello, Judge. My name is Binzi Chang, a first-year postgraduate student from University of Science and Technology of China. My advisor is Professor Li Xi. Today, I'm honored to make a presentation here. The subject of my presentation is the real-time architecture with timing semantics. In the current state of embedded software system, nearly every abstraction has abstracted away time. The instruction set architecture, meant to hide the hardware implementation details from the software, does not include timing semantics for the instruction executions. This results in the lack of timing semantics in software, and the operating systems are hard to perform timing operations. Real-time programs are also suffer from this problem. The key factor to this situation is that the timing of hardware is not preserved during the abstraction. Thus, to address this problem, we try to introduce timing semantics into the instruction set architecture level. And through the ISA, the operating system and program can easily control its timing behavior and achieve more precise timing operations. To introduce timing semantics into the ISA level, we designed a time-triggered instruction set, referred as TTI, based on RISC-V instruction system. Here are some of its instructions. A time register is defined in TTI to describe the current system time. To operate this register, the first two instructions, set TI and get TI, are used. They can read or write this register to edit and get the current time. The other two instructions are IO instructions combined with time. TTI-add perform the read operation at specified time, as shown in the figure below. TTI-add instruction is executed first at time A, but then the read operation is started at the specified time B. It's the same for the TTO-80, except that it performs the write operation. TTI also describes hardware multi-threaded semantics. TTI assumes a table storing all the threads, and they are periodically executed. Two instructions are provided to edit the hardware threads. Take the figure below as an example. Thread A takes 400 cycles to execute, while 200 cycles for thread B. This is how their execution timeline looks like. And TTI introduced timing semantics into the ISA level, but it requires hardware support. Thus, we built a prototype processor called real-time processor, referred as RPU. RPU is a 5-stage classic processor with a configurable number of hardware threads, and it supports the TTI. Each hardware thread takes a set of stage registers and has its own program counter and register file. In this way, each thread is hardware isolated from each other. A thread shader outside the pipeline controls which thread should be executed, and an independent time unit provides the access to the system time. To evaluate the effectiveness of our work, we simulated an anti-lock braking system and had the control program ran on RPU. ABS is a real-time application widely used in cars, and is also suitable for the logical execution time model. The above picture is the procedure of ABS calculation procedure. It takes slip and the vehicle velocity as input and calculates the braking torque. Picture below is the actual simulation waveform, as pointed out in the figure, the thread schedule matches the design algorithm, and time-level operations is done precisely at desired time. Compared with the traditional 5-stage processors, RPU preserves its general performance in real time. RPU preserves its general performance, and in real-time performance, RPU can achieve much better precision. The jitter of the timed I/O operations performed by RPU is only a few processor cycles, while the interrupt-based operations usually require hundreds of nanoseconds. Here we conclude what we meant to do. We built a real-time architecture with timing semantics by introducing timing semantics into the lower level of architecture, the hardware and the ISA level. In this way, we achieve better precision in time I/O operations, meanwhile preserve the general performance. Our work is still in progress, and thorough timing analysis still needs to be done on the processor RPU, and the TDI instruction set still requires the compiler support. This would be the future work. And that's the end of my presentation. Thank you, everyone.
Thank you for the presentation. So questions from the judges, please.
I have two questions. The first one is, how many hardware threads are supported in this architecture?
RPU has a configurable number of hardware threads. In this picture, it is 4 threads. And in the evaluation, the ABS control program, there are 2 hardware threads.
Okay, so if there are like a large number of threads requested, will this cost a significant high hardware cost?
Currently, yes, because as you can see, it copies a lot of resources, such as the age registers and RAID files. This would be a large consumption. Okay.
And my second question is, like even if you use different hardware threads to isolate their interference in the processor, but like different from the application point of view, different tasks may still interfere with each other on other resources. For example, they may compete for the cache, for the memory, and other resource. So how to address the other contentions, other timing interference, in order to make the entire system to be really timing predictable?
That's a very good question, because currently, such as the access to the cache memory, RPU is only a single processor, and the memory it uses is the on-chip memory, like the flash memory or the FPGA resources. And it can, for each thread, it can respond in 1 or 2 processor cycles. Thus, for now, our work haven't deployed, like you said, the competition between the threads in such as DRAM accesses or memory accesses. These will be I think will be our future work to resolve these problems.
Okay, yeah, thank you very much.
Thanks. Also from my side, I had 2 questions, but Nan already asked one, so I just have 1 question left. So the instructions that you add are mostly used to allow a logical execution time. And as far as I remember, because Christoph was my PhD advisor, so he invented LED. So as far as I remember, one of the goals of LED was to allow portability on different hardware and without changing the real-time behavior. So as far as I understood from your presentation and paper, these wait cycles are based on some internal clock. So the duration is relative to the local clock and not to an absolute time, right? So
yes, it's relative.
Yeah. So when I guess then you lose a bit of this portability, right? Because when you port it to another hardware that is faster or slower, but also has support for these instructions, basically the timing behavior of the I/O operation changes, right?
Yes. To this problem, our design was our design would like to take this as a compiler work. Take an example: if the underlying hardware clocks change, the compiler should know it, and it will calculate how much cycles and what the exact number of cycles it will be in the real-time program. And
understood. So you require the compiler support to translate this time into local clock cycles. Yeah.
Yes.
Thanks.
Thank you.
All right. So thank you for the presentation and questions. So we'll move on to the next speaker. So the next speaker is undergraduate student. So we have a mixture of undergraduate and graduate students. Yes. So please start if you're ready.
I hope I'm audible.
Yes, please go ahead.
Yes. I'm Chamika, a finally undergraduate from University of Maruto, and today I'm going to present my work on learning-based attack detection in network-on-chip architectures. So let's first get to know about network-on-chips. We all know the edge computing devices and IoT devices are rising dramatically in numbers. It is believed that there will be 75 billion devices by 2025. The system on chip is the brain of these all devices. When we zoom into a system on chip, we can visualize multiple hardware components working together. For example, it can be processor 1 and processor 2 and GPU running multiple tasks of the same program, such as gaming. With the advancement of technology in the last decade, the number of components inside a system on chip has risen up to more than 100 of intellectual property cores, in other words, IP cores. Network on chip is abbreviated as NOC, comes as the scalable solution for communication as a subsystem within the system on chips. Let's talk about the security of network on chips. The main goal of device manufacturers is to optimize the time to market strategy when they are building a device. For example, people expect all the popular phone companies to release their new models of the flagship phones each and everywhere at the very same time. So these manufacturers outsource the earlier discussed hardware components to third-party IP vendors. This long and distributed supply chain dramatically increases security vulnerabilities, such as insertion of hardware trojans by third-party IP vendors. This raises critical concerns about the security of the node. Two such vulnerabilities are denial of service attacks and eavesdropping attacks. Let me explain these two attacks using 4x4 mesh NOC as an example. In a denial of service attack, an attacker such as a malicious IP in router 1 launches a plethora of packets targeting a victim at 7. These unnecessary packets can cause congestion in networks and can lead to severe performance and energy efficiency degradation. Similarly, if we think about an eavesdropping attack can steal confidential information passing through a NOC when IP cores are communicating. These attackers passively listen to on-chip communications and in an attempt to steal sensitive information with an intention of leaking information over extended period of time. Then I looked into what are the existing methodologies to detect these attacks. There are different types of countermeasures that were previously addressed. One is stop Trojan from triggering, one is latency monitoring, the third one is traffic analysis, and finally statistical profiling. All these methods have produced promising results, but they are fixed for fixed applications and they are not suitable when it comes to application variations in applications or either inputs. Our proposed approach essentially addresses all these limitations. We propose an ML-based attack detection methodology. Our work happens in 3 phases: design time, training time, and runtime. In design time, we craft features and design the router probes in our approach. In training time, we basically train and build the machine learning models offline. In runtime, we use machine learning models to classify attacks within the system in operation. To come up with the approach, we come up with an approach called the collective decision-making strategy. In the collective decision-making strategy, what we do is we collect routers involved in this process and determine whether an attack is placing or not. For example, we aggregate the likelihood of attacks taking place in different places within the NOC and we get the probability value. For denial of service attacks, we consider all the routers because that's where the communication is happening. For eavesdropping attacks, we come up with an approach called the eavesdropping sensing algorithm, where we detect a potentially rogue router and its neighbors, and then we run the machine learning models. This is called the eavesdropping sensing algorithm. These are some of the machine learning steps that we have utilized in our process. And one of the key important things is we extracted features based on position, data, and path, and we engineered features based on hop count, traversal, and count. Our experimental setup was based on GEM5 cycle accurate simulator. We did many training and testing configurations for both these approaches based on different application mappings and input variations. These are some of the two example scenarios. In terms of our experimental results, we explored different machine learning models. And finally, we understood that nonlinear models are performing better compared to the linear ones, with XGBoost having the highest accuracy. After selecting the best machine learning model, we evaluated feature importance and we selected the best features to make sure that there's a trade-off between the overhead as well as the number of features that we are utilizing. Our results show that our approach is capable of detecting attacks with high accuracy in runtime, irrespective of number of placements of malicious IPs and the number of applications running. For our approach, the overhead analysis is 7% and 6% respectively for power and area overhead.
One more minute.
We can conclude as following. Denial of service attacks and eavesdropping attacks are major concerns in the domain of network-on-chip-based system-on-chips. Existing detection methods rely on highly predictable network-on-chip traffic patterns and specific use cases. We propose a machine learning-based attack detection mechanism which can handle diverse applications with input variations and application mappings. Our experimental results demonstrate that our approach can provide runtime detection with high accuracy in wide variety of scenarios with low overhead of 6% and 7% of run power and area overhead. We crafted features that are based for these two attack scenarios specifically. Thank you very much.
Thank you. Thank you for the presentation. So questions, judges, please.
Nan, you want to go first or should I?
Yeah, please go first.
Okay. So I'm interested in maybe I didn't understand correctly, but did you use the same data set for both the training and the testing?
No.
Okay. So what did you use for training the network, and what did you use for the testing and getting the experimental results?
Yeah. So in this scenario, so these are some of the example data sets that I have utilized. So let me zoom into the first iteration here. So for example, here there's in a denial of service attack, there's a communication between IP 0 and 15, and there's an attack happening from IP 1. So for this particular scenario, I'm testing against attack happening in different locations within the network on chip. So irrespective of the placement of the malicious IP, this method can detect an attack.
So these are basically the training data is something that you came up with. It's not like a standardized training data for this type of attacks, right?
So for this, actually, the training data is actually based on the previous research that were done in the domain. For example, this training data is based on some of the work that was previously done for statistical profiling. So based on that, I am coming up with a method using machine learning to detect an attack.
Okay. Thank you.
Okay, so my question is, I still quite worry about the high overhead of your approach, because from the entire system has a lot of security issues to face, and this is just one of them. So you already use such a very expensive solution to deal with it. Then I'm a bit worried if this is really anything practical. Do you have any comments on this?
Yeah, so when it comes to a certain specific scenario, one thing that everyone today is looking into is reconfigurable security within a system on chip. So in this example, let's say that we all use encryption and other stuff when we are doing communication. But if we consider about reconfigurable security, we can isolate a particular set of IPs within a system on chip. And there, we don't need to use particularly encryption. If we have trusted sources, we can directly use this kind of a runtime mechanism. So we can directly get away of the overhead that's happening because of encryption, and we can use plain text here where I have used these features. So that's how I look into that.
Yeah, okay, thank you.
All right, thank you for the presentation and questions. So let's move on to the last speaker of this session, and also the last speaker of the entire SIGVAD SRC. Yeah, Hai-Tao, share your screen and start whenever you're ready.
Okay. So can you hear me, right?
Yes.
Okay, I will start. So hello everyone, welcome. I'm really honored to be here to present my work, a GPU accelerated deep stereo lidar fusion for real-time high-precision dense depth sensing, which was awarded as the best paper in date 2021. So firstly, I would like to talk about the motivation of this work. So for stereo vision, we know that it can acquire dense depth estimation, but they are not reliable. And on the other hand, for the lidar sensors, it can provide accurate and reliable depth measurement. However, the lidar is not able to provide dense information. So actually, these two methods have complementary property for each other. And to achieve these perfect properties, one solution could be fusing stereo and lidar. However, the stereo lidar fusion is not an easy task due to the following three challenges: the generalization, the real-time responsiveness, and the robustness. So, for example, most of currently methods tend to over-specialize to the training site. Therefore, they are not able to address the complex scenarios in the real-world application. Also, the real-time responsiveness and the robustness are also two important aspects for the practical usage of the algorithm. And they are exactly the issues that I handled in my work. So I mainly provide three contributions in the stereo lidar fusion task. And the first one is that I propose a framework which achieves leading accuracy on the unseen scenarios, showing strong generalization. And the second contribution is that the framework is highly computation and memory efficient. It could achieve high throughput with very less memory footprint. And the third contribution is that the framework is also robust to the misaligned lidar input. And it shows little accuracy degradation when handling misaligned lidar data. And here is the overview of the proposed framework. So I utilize a two-stage lidar stereo fusion and the feature fusion to obtain the final prediction. It's worth noting that actually I didn't construct an end-to-end architecture for prediction. Instead, I only use the binary neural network as the preliminary matching likelihood generator. Following similarity metric and the cost aggregation are all interpretable. So they are all general to the stereo vision task, and they are more general to the unseen scenarios. And here is the qualitative results. In the Kitty 2015 designs, the proposed framework achieves comparable accuracy to the state-of-the-art method with an order of magnitude faster runtime and a 3 order of magnitude smaller model. In the ETH3D datasets, we achieve leading accuracy on all accuracy metrics with only 15.9 milliseconds of computing latency. We also show the experiment with the varying levels of misaligned lidar. And the experiment shows that our framework can produce depth estimation with little accuracy degradation, even there is no lidar input. And here is the video demo in comparison with other states with other method. So the image and the lidar input are shown in the first row. The left side are the prediction of the 2 states with other method. And the prediction and the point cloud of our framework are shown in the right side. So basically, we achieve comparable depth estimation results with 2 states of art method. However, our system have a clear lead in running speed. In comparison to counterpart only achieves 1 frame per second. So it's obviously that our system is more practical to be deployed in the real-time application. And here are the practical usage and extended work of this paper. So I published several academic papers with my colleagues by extending the framework of this paper. And I also developed a real-time 3D object detection system by using sparse LiDAR to perform real-time and high-precision detection. Benefited from the robustness of this paper, this system can optionally enable or disable the LiDAR usage to improve the detection accuracy or to save the cost of the whole system. The technology of this paper is also applied to develop a vision chip, which is called the VRI ZM100. And I'm very happy to be able to participate in this project with my colleagues. And I'm really proud that the techniques of this paper have been applied to this vision chip. So this is the end of my talk. Thank you for your time, and questions are welcome.
Thank you. Thank you for the presentation. Questions from our judge panel?
Yes, thank you. I have a question. So I have to admit I did not read the original paper, just a 2-page summary, and I'm missing the intuition on why your method, so having the sequential approach, does not suffer from over specialization in the confined compared to the others. Can you maybe give a bit of an intuition why this is? Because the results look very good, and I'm just it's a bit when the results are so good, I'm asking myself why did the other methods suffer from over specialization?
Okay. So this is really a good question, because this question is also mentioned by many reviewers' comments for the paper. So from my perspective, I think the feature learned by end-to-end architecture from the confined dataset is not as general as ours. So basically, we know that it's true that the end-to-end architecture is extremely powerful. So they can be very accurate for the dataset. But for training the end-to-end architecture, we cannot control the features, what features they learn from the training set. And also because the training set cannot capture all the difficulties in the real world. So learning the high-level features by the network itself in the constrained dataset sometimes could be valid. So for example, if the network could be overfit to the training set, for example, the road scenarios. But if the input becomes the indoor scenarios, the network, because the network never seen this kind of things and this kind of image before, so the overfitted parameters could lead to a inaccurate results. But for our architecture, I think we should refer to the non-end-to-end architecture. Actually, we only use a shallow network, and this shallow network only function as a preliminary likelihood generator. So for any kind of input of the images, the network only measures the similarity between different input images. So even for the images that the network never seen before, it can still telling us that which one is the most similarity patch pair, because this task is just so simple. So it can like general to the different kind of images. So after we obtain this similarity, we utilize the coarse navigation and the refinement components to further improve the accuracy. But these components are all interpretable, and they are all general to the vision task, not only for the constrained dataset. So I mean, for end-to-end architecture, it's relatively easy for them to achieve the high accuracy for the training set and the testing set. But because they learn the features on the confined dataset, their features are like local and high level, and we don't know what the features are. So I think they are tended to overfit to the training side. But for our architecture is so simple, and they are really like.
Hai-Tong, maybe a little bit more brief. There might be other questions. Yeah.
Yeah. Thank you. I think I understood the most.
You are satisfied, Silvio?
Okay. Yes, thank you.
Sorry. Very good. Because there might be other questions. Yeah, and each student 10 minutes to be fair. Yeah. Other questions? Yeah,
I have a question if time allows. So yeah. So I think you did a very good job. I think this is very interesting work. But my question is, Elon Musk says that lidar is a bad idea for autonomous vehicles, right? So he said he will never use lidar on a Tesla. So then, what's your comments on this? What's your opinion?
Elon Musk is not always right. Sorry.
Yeah, of course. This is the reason that now we want to say something, right? Yeah, please.
Actually, I'm kind of agree with Tesla, because for some reason, actually, the lidar is not the intuitive solution for people, because human never know the actual distance of the environment, but we can like drive very well. So but actually, I think this is a like long range object for the whole human being, but it's not the object for ours, because for our generation, I think for this kind of generation, we can it's not reliable for the like pure vision. So only use the cameras, not only use the lidars, the sensors to like measure the actual distance of the environment.
Yeah, okay, thank you.
All right. Thank you very much for the presentation and interesting discussion during the Q&A. If no further questions, I'm going to wrap up this session and also the entire ACM Seedbed SRC 2022. So again, thank you very much for all the students joining us, and especially all the judges. Just for all the students, the outcome will be announced later tonight, okay, 11 p.m. Shanghai time during the ES Week award ceremony, together with other best paper awards, etc. Okay, and then judges, so please, as soon as possible, finalize your scores and send the score sheets to us. Yeah. So thank you once more, all the volunteers, helpers, and everyone. Bye-bye.